Okay, guys, in this video, we are going to talk about directional derivative and what it means. Now, one thing I want you to remember right away is that the directional derivative is the slope of the surface in a given direction. And just like when we had functions of just one variable, the slope was just one number, right? But here, because we have another dimension, you actually can go in a lot of different directions, and each direction will give you a different slope. Because imagine you are hiking, okay, and then you don't just go in one direction, you can go in a lot of different directions, right? So this is the surface. I went ahead and plotted this surface, this example, this next negative x squared y minus 4xy cubed plus 3y squared plus 2x. And the point where we are doing this is at 2, negative 1. So just to figure out what does this directional derivative mean, in the direction of the angle pi over 6, which is like 30 degrees. So what does this mean? So what you do here, so I also plotted the point. So 2, negative 1, I also needed the z coordinate. So I went into the Desmos calculator and I plugged what it was, and it gave me 19 for the z value. So that's my point. As you can see, the red point on the surface, right? But now we want to concentrate on specifically what does directional derivative mean. So I will open this option, this show height to d trace plane option. And here I can actually enter a point that I'm interested in. So that would be 2, negative 1. And it also tells me that that's 19, right? So it shows this here, and then it tells me that's 19, which I already knew. Okay, but now I want to figure out, like, what is the directional derivative in the direction of angle pi over 6 with the x-axis? So to do that, I'm going to go to this little drop down, which is right here, okay? And the option I want here is this one right here, this show directional derivative trace. Okay, so if I click on that, unfortunately, it's a lot of stuff that's going to be displayed. So it's going to be a little bit difficult to understand what the heck is happening. But basically, just disregard this red vector. That's actually, I think, the gradient at that point. And it's weird looking, but just completely disregard it. You don't care. And then the little green arrow, that shows you the direction. So right now it looks like the direction is like 45 degrees or something like that, but we don't want it. We want pi over 6. So I'm going to change this to pi over 6, which is the 30 degrees, right? And so we are saying that if we were to walk on the curve in the direction of 30 degrees, where this little green arrow is like showing you which way you're going, okay, you can see it. Okay, so if you're going in that direction, which makes pi over 6 with the x-axis, okay, angle pi over 6, what's going to happen to the slope? Okay, so what will be the slope in the direction of that green vector? So if you are on the mountain, somebody's saying, okay, go here. What will be the slope? So the slope, as you can see here, shows you that the directional derivative is negative 8.3, right? That's the slope. So you're going down, so you can see the trace. So you're going to go down over here, and the slope would be negative 8 if you were to go in the direction of the green vector. Like if you're going right here, the slope would be negative 8 or something like that, okay? But it is going to depend on the direction, because if I'm going in a different direction, for example, if I went in pi over 2 direction, that's going to be a different slope, right? So then I can see that the slope is now negative 34, so it's going to be like super hard to walk downstairs because it's like very steep. So just remember that directional derivative is a number that shows you the slope of the curve in a certain direction. All right, now let's see if we can start figuring out what's what here. So let me see. How do I find directional derivative? That would be a good question. So the first thing I need to do is find, so let me write down the f of xy. I'm going to find the gradient, which just means partial derivatives, okay? So it's not anything really fancy. We just want the partial derivatives of the original function. Okay, so first, with respect to x. So the first thing I want you to do is concentrate on the terms that have x in them and disregard the other terms. So I have these 3 terms that have x, 3y squared doesn't. So when I take the derivative with respect to x, that's going to go away. Okay, so negative x squared y with respect to x. Think of y as a number, like a constant multiple. You keep it. okay? And derivative of x squared is 2x. So that will be like 2xy. So just like 5x squared would be 5 times 2x, yx squared is y times 2x. Okay, minus, now same thing here, 4 is a number, but also y cube is a number. So 4y cube x is like just number x. What is the derivative? The number. So that would be 4y cube. And then 2x derivative is 2. Okay, so that's the partial with respect to x. So let's do that. Let's type that here. Okay, now let's do partial with respect to y. So now partial with respect to y, only highlight the terms that have y. Otherwise, oh, that's not the right one. Okay, how do I get rid of the highlighting? It just clicks. Okay, how about that? Okay, that works. All right. So this is the also the term that has y, right? Okay, so let's go ahead and find the derivative. So negative x squared y. Now think of x squared as a number. So this is like minus x squared y. It's like number y is the number. So this is going to be negative x squared. Same thing here. 4 and x are both numbers, so you keep them. And then derivative of y cubed is 3y squared. Finally, 3y squared is just 6y. Okay, so this will become negative x squared minus 12xy squared plus 6y. Okay, so I'm going to type that here. And hopefully that's correct. Let's submit that. Okay, the next thing is we actually have to plug in our point, 2, -1, into the gradient. So I hope you forgive me because I am going to do this on the calculator. I am not going to do this in my head. So let's go ahead and type this here. So fx, which is the partial with respect to x, is negative 2xy minus 4y cubed plus 2. I want to know what is fx at 2, -1. Okay, so that tells me that's 10. Now, it does want it in the ij format because you can see ij here, and also it says enter algebraic expression. So it's basically thinking like ing variables. That's why it says that. But you're going to need to enter ing. So this is going to be 10i. And now we want to plug in the same thing we're going to plug in into the other derivative. So let's enter that and plug in the point, and we get negative 34. So that would be our gradient. That's why it was so long. Remember that vector was like huge. It went like when I was plotting it, that red vector. Well, this was a different direction anyway. So it's too late. Anyway, that's your gradient. Okay. What's next? Next, you need to find the direction vector. So how do you find it? Well, that actually depends on whether they give you the angle with the positive x-axis or they gave you an actual vector, direction vector. So in my case, they actually said, okay, the angle. So they just said, okay, theta equals pi over 6. So how do I find this direction vector? Now, one thing you should always remember is that the direction vector should always be normalized. What that means is that its length must be 1. If it's not 1, it's not good. Okay, so you're going to have to divide it by the magnitude to make it 1. However, when you have an angle, the direction vector is going to have components as cosine theta and sine theta. Well, actually, let me write it using ing notation. So it's going to be cosine pi over 6 is going to be the x component, and sine pi over 6 is going to be the y component. Okay, and this vector already has a unit length, meaning length of 1. Why? Because cosine squared plus sine squared is 1. So if you try to find the magnitude, you will see that that's just going to be 1. Okay, and so I do not need to normalize it, but I do need to know sines and cosines of basic angles. Now, if you don't remember what they are, but at least you remember that they should be something like square root of 3 over 2, or 1/2, or maybe square root of 2 over 2, well, just use Desmos, but you do have to want to switch to radians. So cosine pi over 6 sine pi over 6. So you can kind of like wink it and say, oh, of course I know that sine of pi over 6 is 1/2, because Desmos just told me that. But okay, so that's actually the y coordinate. This one, this weird 0.866, that's, I bet you that's square root of 3 over 2. So if we look at that, yes. So we know cosine is square root of 3 over 2. So we pretended we know the trig circle. And not every teacher is going to be so nice to give you Desmos, so you might have to memorize that stuff. Okay, so this is my direction vector. And then the final step is to actually find the dot product of the direction vector. So this is square root of 3 over 2I plus 1/2 j. So we want to find the dot product of the gradient after we plugged in the point, dotted with this u, vector u, which has to have unit length. Well, hopefully you already remember what is the dot product. So you just multiply the x components. It's not a vector. Remember, directional derivative is a number. It's the slope. It's not a vector. So, and also dot product is not a vector. So this is going to be 34 times 1/2. Now, a little bit of a simplification, 10 over 2, that's 5. 34 over 2, that's 17. So I think that would be it. If you needed to find the actual value, you can plug that into the calculator. So that's going to be 5 square root of 3 minus 17. So it's negative 8.3, something like that. If you remember, that's what I got when I was doing this, but then I changed the angle. So the angle of pi over 6, that was the trace, and then it's the same, as you can see. And it also shows you the unit vector. So it's approximately 0.87, which was the cosine of pi over 6, and 0.5 for the sine of pi over 6. So that's the story of the directional derivative.